Hello everyone, I'm Shuai from University of Connecticut. I'm here to present our work, information retrieval based for localization for concurrent programs. It's a joint work done with my supervisor, Professor Tingting Yu. First, let's take a brief look at how information retrieval based for localization, LFL, works. The basic idea of LFL is to calculate the similarity between bug reports and the buggy program. Bug reports are used as queries to measure the similarity between each software entity and the bug report. The ranking results, which are based on the similarity scores of the software entities, indicate their relevance to the bug report. Although LFL has been extensively studied, none of the existing approaches have focused on concurrent program. So we proposed an approach by considering domain knowledge to build a knowledge graph to represent the concurrency bug. We applied a term weighting algorithm on the knowledge graph to identify the important tokens as a search query for LFL. Here's an overview of our approach. Given a project and its source files, we first create and index them as a corpus. Second, we parse the bug reports by using several natural language processing techniques. And after parsing the bug reports, we build a knowledge graph to represent the information. Then we utilize a term weighting algorithm to identify important tokens as a search query. Finally, we apply the search query to a retrieval model to retrieve and return the ranking results. First, for the corpus creation and indexing, we have 4 steps, including word tokenization, stop word elimination, program keywords removal, and concatenation word splitting. For example, here's a code entity type declaration will be separated into 2 individual words, like a type and declaration. We have 3 steps for bug report parsing. First, we identify and extract key entities which are related to the bug or source code. And then we parse each sentence into dependency graph based on their semantic relationships. We also apply the co-reference resolution to determine whether 2 or more words refer to the same entity. After the bug report parsing, we will build the knowledge graph upon the dependency graph. For domain-specific knowledge graph, one of the key steps is to identify concept types and the relationships between each concept. The concept typically represent entities or objects in the domain we are modeling. In our work, we define 9 different concept types based on their meanings. For example, the words like dialogue, risk condition will be categorized into the concept type called the concurrency bug. After we have these 9 concept types, we modeled 7 concept relations to capture the meaning of a concurrency bug and extract key information. Let's have an example here. Here's a dependency graph for the sentence which described a dialogue scenario. First, we identify concept types from this sentence. That, like dialogue is a concurrency bug, the thread is a concurrence mechanism, the servlet output stream is a code entity. After we have these concept types, we find 2 concept relations. The first concept relation is between concurrency bug and the code entity. So the 2 concepts will have an edge. Another concept relation is concurrency bug and concurrency mechanism. So the 2 concepts will also have an edge. After adding edges for concept relations, we remove or replace the edges from the original dependency graph. So here we have a knowledge graph. We then use the term weighting algorithm like PageRank on the knowledge graph. Then each token in the knowledge graph will have a PageRank score. We select the important token according to the score as a search query. Finally, we apply the search query to the retrieval model to retrieve and return the ranking results. To evaluate our approach, we selected 692 concurrency bug reports from 44 open source projects. To make our evaluation clear, we classified bug reports into 4 different types based on existing works. Since program entities are always considered important information, bug reports that have program entities in their descriptions will be classified as dataset PE. However, the stack trace information are always considered noise information. So the bug reports that have program entities and also have stack trace information will be classified as dataset PES. The bug reports that only use natural language without any programming entities will be dataset NL. The dataset NLS stands for dataset NL with stack trace information. We compiled our approach with 4 baseline techniques. The baseline query BR text is generated by only considering text description in a bug report. The baseline entity is generated by extracting entities that belong to the 9 concept types as we defined before from a bug report. By applying PageRank algorithm on only dependency graph instead of the knowledge graph, we have the baseline query DIN graph here. The baseline GPT is the query generated by ChatGPT. We give ChatGPT a bug report and ask ChatGPT to generate a search query for the information retrieval for localization. Our approach here called BL Collier. The results show that BL Collier outperformed all baseline techniques with higher scores, which indicate our approach could identify important information by using a knowledge graph with domain knowledge. The queries generated by ChatGPT is similar to our baseline entity, but GPT will also select irrelevant entities which are not in our defined concept types. Sometimes will lead to a low performance. We also compared our approach with 6 state-of-the-art LFL techniques. Our approach outperformed all other techniques on dataset PE, but for dataset PES, our approach doesn't have a certain method to analyze the stack trace information. And the state-of-the-art technique BR Tracer here has a stack trace analysis method. So we'll adopt the BR Tracer's method for BL Collier to analyze the stack trace, called BL Collier Plus. The results show that BL Collier Plus performed better than other techniques on the dataset PES. In this work, we proposed a novel LFL technique called BL Collier by using knowledge graph with domain knowledge and the information retrieval method to effectively pinpoint concurrency bugs. In the future work, we like to focus on finer grained for localization at the method level. Okay, thank you for the listening.